Let's create a little bit more of a complex example than what we did in the last time. So in this particular case, let's just take an example network consisting or that looks like this, right? So we have an input layer, that's what we call this as, and these are hidden layers. The last layer we call it as an output layer, and matrix dimensions depends on the way how the framework computes the um, forward network or backward propagation. So TensorFlow tends to do the matrix dimension as input times the the output of one layer to the input of the next layer. So in this particular case, it's 2 by 3, and this is 3 by 3, and then this is 3 by 2, which is okay. It depends on the way how you do the matrix multiplication. In neural networks, most of the times when you think of deep layers like this, you just need to take any two pairs and understand that pair just to understand everything what's going on. So in this particular case, I'm not making any connections. You can imagine that all these things are connected to all the other nodes because these are dense layers. And let's see how we can code this in Keras. So here is a sequential model. As you can see, these are layers that are stringed together from one layer to the next layer. So the way how you would create is, here is a model, tf.keras.models that sequential is a model. There are different ways that you can create a model. This is one of the ways I am showing it here. You can pass in the array of layers as well. Don't worry about if I don't understand what I just said. So once if you create the model, you add a dense layer of 3 because as you can see, the first layer we said, hey, it's a layer of 3 with the input shape of 2 because the shape is 2. Right? And then the next layer we string together another layer by adding the additional dense layer with 3 nodes, and then finally we string together a dense layer with 2. And then that's you're creating a model. You created this model using this code. Once if you do that, let's take an example just like the last time. We take 1, 2, and then pass it through the network. And from last time, you must have convinced that the matrix multiplication feed forward, the way how you saw the output was convincing enough. So we are not going to go through the calculations. We assume that the framework is doing the right calculations, and then we pass that input through this model and we get some output. The output happens to be 2, which corresponds to the 2 outputs from these output layers. So in this particular case, we also added a different activation layer, ReLU, and the output is softmax. Again, these ReLU and softmax activations don't really make any sense for now for this example because I'm just demonstrating how to string the layers together. Right? Now you can take the model and compute the model weights. As you can see in the first one, we have the shape of the weight is 2 by 3. That's what you see here. Next one is 3 by 3. And then we have the bias, which is shape of 3. This is the funny shape in Python without the second index, which means it is just an array. And finally, we should have the weights for the last layer to be 3 by 2, which is 3 by 2 right here, as we expected. So once if you understand any 2 layers, how the computation works, it's the same thing. So we can also take the layer weights as well. And then model summary will give you each of the layers and number of parameters. Let's calculate the number of parameters in each one of them. So for the first one, it is we have a 2 by 3 matrix, and then 3 bias. So counting that, we should have 9. So 9 is the total number of parameters. For the next one, it's 3 by 3, which is 9 plus 3 for the bias. So that's 12. And for the last one, it's 3 by 2 and plus 2 for the 2 bias terms here. So that's 8. So total number of parameters is 29. So it's not unusual to see millions of parameters in a deep neural networks. So again, deep neural networks means lot more layers, lot more nodes in each of the layers, and then computation should be as simple once if you have created a mental model right now. So here is the next example that I have seen. I've shown here. This is not the way how you would pass each row through the dense layer. This is just an example. Most of the times you would batch a certain set of inputs and feed it through the batches, and one pass through the entire training example is called as an epoch. Now let's take one example. So it's batch of 1, right? So it's 4 and 0.5, and again you can imagine all these connections happening through all the nodes, and feed forward happens through multiplying these matrices, creating new tensors, and output you expect to be 67, whatever the output you get, because the weights is going to be y hat, the predicted value, and based on the loss function, the backward propagation happens. Those things you must know. This is the implementation, how you're going to implement the deep neural networks, but not the theory aspects of the back propagation for feed forward propagation. So that's in essence all you need to know about how to build layers. So let's take some more somewhat realistic example and build a network and see what's really happening. So in this particular case, again, I have a sequential network, and the first part of the network, it has the shape 3, right? And it has one input that's connected to all these 3, and then these 3 is connected to one output in the second layer, and then this layer has the activation of ReLU. This is the activation of linear for this layer. And then we are using the SGD optimizer, stochastic gradient descent, with the loss of mean squared error. So I have created an artificial input where you can see the input is one dimensional, output is somewhat has multiple segments of linear segments, and this is just to show that ReLU will adjust itself for each one of these segments and computes the output or the weights for this neural network to do reasonably pretty good approximation of this function, linear piecewise function. Let's see if it works. So that's the same thing that we've seen, and then I'm using what's known as TF dataset from tensor slices, because what we created the input and output as NumPy array, TensorFlow uses its own data set in its own data structure, and that you can create by using this particular call. Don't really worry too much about it. If you don't use it, it has to convert each of these NumPy arrays into TensorFlow, and then there'll be a warning that you might optimize it. So I just created that here. We are going to talk about more about data sets in the upcoming videos. So I have epoch 250 to see if how it would perform with 250 epochs. It should be pretty quick. So once if I do that, let's take a look. It's not bad, but it could do better. So as you can expect, model summary, the first one happens to be 6. Easily you can count it. It is 3 times 1 plus 3 for the bias. The second one happens to be 4 plus 1 is um, 3 plus 1 is 4, because you will have a bias term right here. So it is just getting used to counting the number of parameters until you are comfortable with it. Let's just increase the training to 4 times and see what happens. Hopefully it's going to get better. As you see last time that I have already run this, so it's getting better with the piecewise linear activations. With ReLU being the activation function, it automatically adjusts itself to bec- to create a model that's more and more closer to the piecewise linear approximation for the actual output. So that's about what you need to know. So with this, the layers and creating dense layers and ReLU functions and activation functions with different kinds of optimizers, you can build quite a sophisticated set of neural networks. So we'll get to talk about few additional things such as TensorBoard and different kinds of callbacks, that way you can save the model and retrieve the model in the next upcoming videos.